Yes, same color guy. For cyclophosphamide, this is its structure. This is the cyclophosphamide. This drug is a prodrug, meaning it should undergo metabolism before it becomes active. It should be metabolized. Active drug. It's a chiral at this group. It's chiral because we have 1, 2, 3, 4 different atoms attached to the phosphate group. This drug, it undergoes activation first by the CYP450 enzymes. We have the CYP2B6 as the main enzyme for its activation. We can also have the CYP2A4, but mainly it is CYP2B6. This one does the hydroxylation of this drug. We have this. We shall form this is carbinolamine or the hydroxy cyclophosphamide. It is hydroxylated at the position 4. This is position 1. This is 1. This is position 2. This is position 3 and 4. At the position 4 of the ring, it is hydroxylated. After hydroxylation, we shall have the hydrolysis of the drug. Form this. We shall have this N, H2, and this. This is carbon 1, 2, 3. We shall have that due to hydroxylation of hydrolysis of the drug. We shall have this. This is the aldophosphamide. This drug, after hydroxyl or hydroxylation, this one can be transported into the cells, the cancer cells. Before hydroxylation, the drug is not able to enter the cancer cells, but after hydroxylation, it can be carried into the cancer cells. If this one happens outside the cell and we form this one can also be carried into the cells. This one can enter into the cells, but this one cannot. Then, after forming this, we shall have hydrolysis of the drug, getting this. Here, remember we have a hydrogen atom at this position. When this one takes these bond electrons, we shall have loss of the hydrogen atom to stabilize this hydrogen here shall be lost to stabilize this carbon, which is losing the bond electrons. We shall have formation of this. This is the phosphoramide mustard. And this is the active drug now. This is the active drug. Before breaking this ring, the drug couldn't form the azidine cation, but after breaking the ring, this drug can form the azidine cation. Hence, we can alkylate the DNA. And we shall have also formation of this, the acrolein. This group, this is acrolein. Acrolein is nephrotoxic and urotoxic. It can damage the kidney and also the urinary tract and the urinary tract. We are going to deal with this one after. Then this drug, it stays as iron because of its pKa. pKa is around 4.75. It's pKa. Meaning that at the physiological pH of the 7.4, around 7.4, this drug will stay as the ion. So it is trapped into the cell. It will be trapped in the cells. When it is trapped, meaning that it can now alkylate the DNA. You can form this. We form the azidine cation. This azidine cation, as the N takes the electrons back, we shall have the nucleophile, which is the N7 of the guanine. This one is attached to the DNA. So we shall form this with the nucleophile now attached. And this nucleophile is on the DNA. It is the same mechanism for also this mustard arm. We shall form nucleophile after forming the azidine cation. And this nucleophile is on the DNA. When DNA is trying to be liberated from the covalent bond of the nitrogen mustard, we shall have damaged DNA. We shall have two DNAs, but they are damaged because they are losing the guanine. Hence, we shall have this structure here. With the nucleophile. Also, this we shall have the nucleophile attached. And this one will exist as a protons like that. Then the chloride will be present also. This one will be plus, then chloride will be present. This is the activation mechanism for the cyclophosphamide. We can have inactivation of the cyclophosphamide at different stages. I think we should grab this and do the inactivation mechanisms for the cyclophosphamide. And also, this Acrolein is very toxic. It's very toxic. The antidote is mesna. Let's see the structure of mesna and how it is used to counteract the effect of the Acrolein. Yes, MK the guy. As we said, that cyclophosphamide is a prodrug and its activation involves the CYP450, where we have the CYP2B6 as the main enzyme for its activation, but also the CYP3A4 can activate the drug, giving us the hydroxylated drug. This is the hydroxycyclophosphamide. Or it's called carbinolamine. Then this drug undergoes hydrolysis from this, which is the aldophosphamide. And this aldophosphamide gives us the Acrolein. And phosphoramide mustard. Now this one is the active drug, which will alkylate the DNA. And this Acrolein, we say that it is nephrotoxic. And urotoxic. It can damage the kidney and also the urinary tract. We say that this is the activation, but we have the deactivation of the drug, where you can have this mechanism here. Down here, we can move the mustard arm and we can get this drug or this metabolite. Here there is H. We can get this metabolite, or we can get this when both arms are removed. We can have this. This is the alkylation. Here we shall lose this group called the chloroacetaldehyde. Chloroacetaldehyde. And this group is also nephrotoxic. This group is also nephrotoxic and neurotoxic. It can cause seizure and mental retardation when it crosses the blood-brain barrier. This group, the chloroacetaldehyde. So this is one of the mechanisms, and here it involves the same enzymes which activates the drug. They can inactivate the drug, the CYP3A4 and CYP2B6. Then here we can also have the activation at this point. Here the activation is by the alcohol dehydrogenase. Alcohol dehydrogenase It deactivates the drug. The OH group now becomes the keto group. It becomes the keto group. This is one of the deactivation mechanisms also by alcohol dehydrogenase. This is inactive. And also these ones are inactives. At this point, also we can have the, now this one will be the aldehyde dehydrogenase. This is alcohol dehydrogenase. This is aldehyde dehydrogenase. This one will lead to oxidation of this group. We shall have this. We shall have oxidation of this group. Instead of the aldehyde, we have the carboxylic acid. And also this one is inactive. Those are the three ways to inactivation of the cyclophosphamide. Now, this Acrolein, it is nephrotoxic and urotoxic. This can be counteracted by the mesina. In presence of mesina, we can form an inactive, highly water soluble metabolite. Now, this is our Acrolein. This is the structure of mesina. This is the mesina. Now, mesina will attack this carbon. This one will take the proton. We shall form this. We shall form this. This is an ester. This ester is highly water soluble and can be eliminated through the kidney. So, mesina can prevent the urotoxicity. But for nephrotoxicity, since this mesina is highly water soluble, much of it will concentrate in the blood. Much of it, not in the kidney, but in the blood. So, this mesina can treat the urotoxicity, can prevent the urotoxicity. But it's not much important in nephrotoxicity, meaning that Acrolein can cause the nephrotoxicity, but urotoxicity can be prevented. But nephrotoxicity is not easily prevented. For nephrotoxicity, the glutathione is enough for nephrotoxic effect. But if the drug concentration increases, of course, it can counteract the glutathione. If the dose increases, then we have the nephrotoxicity. But at normal doses, glutathione alone is enough for that effect. Also, the chloroacetaldehyde. This one can cross the blood-brain barrier. This is the chloroacetaldehyde. Also, mesina has limited effect on the chloroacetaldehyde. But glutathione can also overcome its effect. But because this one can cross the blood-brain barrier, can lead to serious side effects like seizure and mental retardation. The chloroacetaldehyde. Yes, guys, let's go to ifosfamide. We see how is it activated and how is it deactivated.